Hi, welcome back to my channel Math Caffeine. This is the introduction video for the next series, Quadrilaterals and Other Polygons. It includes all the theorems and corollaries necessary for this series. There's a lot, so let's get started. The first theorem to know is the polygon interior angles theorem. It states that the interior angles of any convex polygon with n number of sides can be calculated using the formula the quantity of n minus 2 multiplied by 180 degrees. For example, a triangle has 3 sides. When you plug that in, you get 3 minus 2 times 180, which is just 1 times 180, giving it a sum of 180 for its interior angles. If we look at a pentagon, it has 5 sides. Plug that in and we get 5 minus 2 times 180 degrees, which is 3 times 180 degrees. Therefore, the sum of the interior angles of a pentagon is 540 degrees. There is a corollary that goes with the polygon interior angles theorem. It states that the sum of the measures of the interior angles of a quadrilateral is 360 degrees. We know this to be true because of the theorem we just learned. Remember, a corollary is a statement that can be proven easily using the use of a theorem. The polygon exterior theorem states that the sum of the measures of the exterior angles of any convex polygon is 360 degrees. If we look at a pentagon, the arrows point to where the exterior angle is. These angles go around any polygon, therefore its angles add up to 360 degrees, or one full circle. If we look at the quadrilateral, we can say the same about its exterior angles. They add up to 360 degrees. The parallelogram opposite sides theorem states that if a quadrilateral, or a shape with 4 sides, is a parallelogram, then its opposite sides are congruent. Looking at this example, we are given that this quadrilateral is a parallelogram. Therefore, we can conclude that AB is congruent to CD and AC is congruent to BD. This theorem is very similar. If a quadrilateral is a parallelogram, then its opposite angles are congruent. If we look at this example and we are given that quadrilateral ABCD is a parallelogram, then we can conclude using this theorem that angle A is congruent to angle D and angle C is congruent to angle B. The parallelogram consecutive angles theorem is closely related to the consecutive interior angles theorem, which states that if two parallel lines are cut by a transversal, then the pair of consecutive interior angles formed are supplementary. For example, if we look at these two lines, parallel lines, cut by a transversal, we can conclude that angle 1 and angle 2 are supplementary, or add up to 180 degrees. If we look at the parallelogram, the theorem proves that angle B and angle D are supplementary because AB and CD are parallel lines cut by the transversal line BD. Theorem 7.6 on parallelogram diagonals state that if a quadrilateral is a parallelogram, then its diagonals bisect each other. Remember, bisect is to divide into two equal parts. If we look at this example, we know that a quadrilateral ABCD is a parallelogram. Therefore, we can conclude that when diagonal BC and AD are drawn, that point E bisects AD and BC. The length of AE is congruent to the length of DE, and the length of BE is congruent to the length of CE. Theorem 7.7 is about the opposite sides of a parallelogram. It is the converse of the parallel opposite sides. This time, if we can prove that the opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Note that in these two figures, a rectangle and a parallelogram, opposite sides are both congruent. Therefore, they are both parallelograms. AC is congruent to BD, AB is congruent to CD. EF is congruent to GH, and EG is congruent to FH. Theorem 7.8 is another converse theorem, where if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. For example, if we know that angle A is congruent to angle D, and angle C is congruent to angle B, then quadrilateral ABCD is a parallelogram. In quadrilateral EFGH, If we know that angle E and angle H are congruent, and angle F and angle G are congruent, then we know that it also is a parallelogram. In Theorem 7.9, if one pair of opposite sides of a quadrilateral is congruent and parallel, then the quadrilateral is a parallelogram. For example, if we know the side AB is congruent to and parallel to side CD, then we know that quadrilateral ABCD is a parallelogram. This theorem is the converse of the parallel diagonals theorem and states that if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Looking at this example, we can tell that point E bisects AD and BC and intersect AB and BC at point E. Therefore, quadrilateral ABCD is a parallelogram. We are now going to look at three corollaries that prove when a quadrilateral is a rhombus, rectangle, or square. The first one proves a rhombus. A quadrilateral is a rhombus if and only if it has four congruent sides. If we are given that all four sides of these three quadrilaterals are all congruent, we can conclude that each of these are rhombi. This corollary states that a quadrilateral is a rectangle if and only if it has four right angles. In the case of a rectangle, we know that only opposite sides need to be congruent. Having four right angles keeps the lines perpendicular, therefore it is guaranteed to give congruent opposite sides. The final corollary states that a quadrilateral is a square if and only if a rhombus, meaning it has four congruent sides, and is a rectangle, meaning it has four right angles. The blue quadrilateral is a rhombus because all four sides are congruent. The green quadrilateral is a rectangle because it has four right angles. Combining them, and we get four congruent sides and four congruent right angles, we know that this is a square. In Theorem 7.11, it states that a parallelogram is a rhombus if and only if its diagonals are perpendicular. In the figure, the two red lines create four right angles, meaning they are perpendicular diagonals. We can conclude this image is a rhombus. In Theorem 7.12, we can prove that a parallelogram is a rhombus if and only if their diagonals bisect a pair of opposite angles. The red lines drawn in the figure cut each angle in half, so this parallelogram is a rhombus. In Theorem 7.13, if a parallelogram diagonal are congruent, then it is a rectangle. In this example on the left, the two red lines are congruent, so we know that this is a rectangle. In this example on the right, the lines are not congruent. As you can see, this one is longer than this one. Therefore, we know that this parallelogram is not a rectangle. An isosceles trapezoid is a quadrilateral with two different length bases, but two congruent legs. Theorem 7.14 states that if a trapezoid is an isosceles, then each pair of base angles is congruent. For example, angle A is congruent to angle B, and angle C is congruent to angle D. The converse to the isosceles trapezoid base angles is that if you already know a quadrilateral is a trapezoid, you can prove that it is an isosceles trapezoid by showing the pair of base angles is congruent. Like if you prove that angle C and angle D are congruent, or that angle A and angle B are congruent, then you can conclude that quadrilateral ABCD is an isosceles trapezoid. Theorem 7.16 is the isosceles trapezoid's diagonal theorem. It states that a trapezoid is isosceles if and only if its diagonals are congruent. For example, this quadrilateral is an isosceles because segment AD is congruent to segment BC and the diagonals of the trapezoid. Trapezoid midsegment theorem shows that the midsegment CD, which is a segment created by the midpoints of side AE and side BF, is parallel to each base, in this case base AB and base EF, and the length of it is half the sum of the length of base AB and EF. A kite is a quadrilateral that has two pairs of consecutive congruent sides, but opposite sides are not congruent. Therefore, this line and this line are congruent, this line and this line are congruent, but the opposites are not. The kite diagonal theorem states that if a quadrilateral is a kite, then its diagonals are perpendicular. As you can see in this image, this quadrilateral is a kite, so we can conclude that the red lines, these diagonals, are perpendicular. The final theorem for this series is the kite opposites angles theorem. It states that if a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. For example, in this image, we know this is a kite. Therefore, one pair of opposite angles, like BD or AC, are congruent. That wraps up the theorems and corollaries for Chapter 7. If you have any comments, questions, or concerns, feel free to email me at mathcaffeine@gmail.com. Happy studying!